So we're moving slowly. So after the aggregate result, now we want to move on the decomposition. And before we go on theta, I will just very briefly show you and remind you how to do the decomposition and the different properties. Some of the things that I will show now, some of them you already seen that James was on Tuesday. But I will get back to that to make sure that in the whole process of developing the MPI, all of these different steps are very well understood. So the main focus on the lecture is on two things. The first is the population subgroup decomposition and then dimensional breakdown. But both are related to decomposition of the MPI result. So you can decompose or disaggregate the result by population subgroup or by dimension or by indicators. And in population subgroup, you can have different type of subgroup. It could be geographical groups like region or district or anything on administrative like decomposition of the country. Or it could be any other social groups like ethnic groups, income. You can even use different income groups, monetary income groups to see, for example, how it's related to what you're getting in MPI. It could be gender decomposition. You want to see how men perform versus women. So in population subgroup, you can have different groups depending on what you're analyzing and what is relevant to your research. And the dimensional breakdown basically is to try to tell you what is the composition of poverty. So once you agree that this is my measure of poverty, so what are the contribution of different phases or different aspects of poverty in the overall situation. And this is also useful because it tells you more or less where are the challenges in terms of countries' evolution. And of course the reference again, the Office books is in chapter 5. When you go there, you can see in more detail all of these things. So let's start with a practical example. So assume that you have this multidimensional matrix of achievement for 3 dimensions. So you have income, education, and health, and you have 3 individuals. So in terms of population subgroup, we can say, for example, these 2 first groups, they are one group of the population. That could be one of the region of this country, or this could be men. And then the second group, you have the third individuals. And the hypothesis behind this subgroup decomposition is that the groups are exclusive and exhaustive, meaning that if you sum 2 plus 1 here, you have to get the total number of population. So in general, for a group, if the group 1 has a population size of N1, and the group 2 population size is N2, so N1 plus N2, you have to get exactly the total number of population, which is N. So you will not do the decomposition. This is why basically the decomposition is, because if by putting together you have different groups, you have some intersection or overlap, so all the properties that we are talking about here will not apply. So if that's the case, there is these very nice properties, which is population subgroup decomposability in poverty analysis, meaning that if you have a poverty measure P, your measure is decomposable, satisfy the population subgroup decomposability if you can write it in that way, which is an average, a weighted sum of the poverty in each of the groups. So in the case of 2 groups, so that means that your level of poverty in overall population equals poverty in 1 times the share of population in 1 plus poverty in 2 times the share of population in 2. And if your poverty measure satisfies this, so you can compute this contribution of the groups in overall poverty, which is basically just what is the share of this block into overall poverty. Or is this, so the share of population in 1 times poverty in 1 divided by poverty in the total population. So this population subgroup decomposability, the MPI or M0 satisfies. And this is what we will check. We will not get into mathematical demonstration on how we get the decomposability with M0, but let's see in practical way how it's come. So we have here 4 dimensions and 4 individuals, and here you have the deprivation cutoff. For the income, the person is deprived if his income is less than 500. In year of schooling, the person is deprived if his year of schooling is less than 12 years. And in improved sanitation, you have directly reported if the person have improved sanitation or not. And here we have access to electricity, which is the same. And then from the matrix of achievement, this is something that you already now know. You can even play around with it, even with closed eyes. So, but I'm just, going back to that just to make sure that we're following all the steps. So from matrix of achievement, we get the deprivation matrix, which is, we put 0 for people who are not deprived in that indicators or dimension, and 1 if the person are deprived, which is very straightforward from what we have here. And from here, we get the weighted deprivation matrix, which is the 3rd step that you're already also very familiar with now. So you use the weight vector, which is in a relative, the normalized weight vector here. Sometimes you see it's not normalized, but you have to pay attention to that. So if you use the normalized weighting vector, so then you have to use also a normalized poverty cutoff. And then you get the weighted deprivation matrix, which is just you take the weight vector, you multiply to the deprivation matrix, and you get this.
So what do you mean by normalized?
Meaning that you're thinking in relative terms. So the weight is like the sum of the weight. If you take the sum, you will get 1 instead of getting the number of dimension or indicators. Because sometimes it's written in a way that if you sum the weights, you get the number, the total number of indicators. So once you have the weighted deprivation matrix, now we want to identify who is poor using a K value of 3/8. And to do this, I think there is a step that definitely this person is not poor because he's not deprived in nothing. And this one, what is his C vector? 3/8. So he is poor, right? And this one,
he's poor. Yeah, poor as well.
but what do you get for him? Is 2 plus 4, 6, plus 1 plus 1 is 1,
Yeah.
right? And this one you get 4/8. So these 3 people, they are poor. Now, how do you do the decomposition here? This is, so if you calculate the M0 for this, so this one we said his C vector is 0. This one you said is 3/8. And this one is 8/8. And this one is 4/8. So if you take the average, you get the 15 over 30 true. So if you compute the M0 for this matrix, you get 15 over 32. So now let's see if the decomposability is satisfied here or not. So assume that you want to do the decomposition of this population in two. The first group in pink, you have 2 persons, and the second group in green, you have there is 3. And then we compute the M0 here and another M0 here and see if we take the average sum, we will get the initial M0 and if the M0 indeed satisfy the population subgroup decomposability. So if we compute the M0 for the pink group, we get, what do we get? It's just a 3 over 16 because now you're not taking the average over the entire population, but you're taking the average of these 2 CI vector, but for 2 persons, right? Because if you want to get the M0 for the pink, you will ignore all the rest. You will just think as you have 2 persons for the 4 dimension. And then we get 3 over 16, which is basically the 3 over 8 here plus 0 here divided by 2. Okay?
Mm-hmm.
And then you compute the M0 for the green group, which is the 8 over 8 plus 4 over 8 divided by the 2 person, because the M0, remember that the M0 is the average over the entire population of your CI vector or of your weighted deprivation matrix. Some sort of one. Okay? Here is easy because the first person is, or he's non-poor and he's not depriving nothing. So this matrix is at the same time the Sanskrit one also, which is another step that you have to do if you have anyone who is not poor. But here we're not doing that because it's already Sanskrit, because it's not depriving nothing already. Okay? So if you compute, then you get the M0 for the green is 3 over 8. So what is the overall M0 using the decomposability equation or formula?
15 divided by 32.
So it's going to be
1/2 times 3 over 60.
1/2, because the share of your population of pink group is 1/2 times their M0, which is 3 over 16, plus 1/2 will be the share of population of group 2 times their M0, which that gives you exactly the initial M0 we calculated. So this, we're getting this with this very small matrix of 4 times 4. So with the data set that you have, which is, I don't know, 1,000 or several thousand times another 1,000, you will get the same. And for those who are interested in how you get, how you show the decomposability property of M0, you can get into the book. You will see all the demonstrations there, which are, we think that is not really needed to present here, but what you need to keep in mind is that the M0 satisfies the population subgroup decomposability, meaning that if you take your population and you divide, you form different groups. It could be geographical group, economic group, social groups, or any other mutually exclusive groups that sums to the total number of population. You can apply all of these formula to get the contribution of each of the groups in overall poverty. Okay? So now, if you want to get then the contribution of group 1, and then we take again the formula, the share of group 1 times M0 in group 1 divided by M0 in total population. So that gives you the contribution of group 1 to overall poverty. If you do that in geographical decomposition, you will get, for example, the contribution of one of the states of, I don't know, US in poverty in US, for example. And same for the second group. Why that all of these things are important? Because if you just want to compute, you can get, so it's important because it's very useful from a policy perspective. So for example, when you take the case of a country like Nigeria, when you compute just the MPI in Nigeria, you get 0.240, for example. If you don't do this decomposition, you just have a very like black, very aggregated number that you cannot do. Maybe you will use, let's say, the Nigerian government, if they have a budget to fight poverty, they will end up spending too much money in certain part of the country where it's not really needed. So this is something, but the second thing is also, usually, if it's possible to decompose, it's always possibly good to do it, because the more you have information usually in policy analysis and in statistical analysis, the more you have information, the better is what you're doing, right? So if you decompose, you will see that Nigeria from one region to another region is a completely different, you get different, you have some region like this one where you have almost no poverty, and the other region in that where almost all the poverty in the countries are there. So when you have this, so that you can say, okay, so at least I know where are, the problems and which groups I have to focus on. And here is there are geographical groups, but you can do also the same to say, okay, in US maybe most of the problem comes from these social groups. So then when it's come to like designing certain development agenda or policies, you know exactly which groups of the population you have to focus on. But if you don't do that, you just get a numbers that aggregate everything that you can use depending on the context, but in most of the situation, you need to know really how variable are your poverty figures. So then you see at the national is 0.24, but if you do subnational analysis, the MPI varies from 0.04 to 0.6, which is a very big interval in which you will get the national number, but it's very huge from one region to another region. Another example is the case of India, which has the MPI of 0.2, but with a very high variability between the different regions of India. And you can do this by using the absolute numbers, which is MPI here, or you can also do it to analyze to analyze changes over time and decompose the result to see so I'm trying to say you can do it in absolute or in changes term. You can try to get a poverty map just with the MPI figures, or you can also try to see how poverty has changed for different regions or for different subgroups and so on. So in the case of India, for example, a paper that Schumann and Sabina did in 2013, they finding, for example, that most of the reduction of MPI in India has been driven, for example, for the region which were initially non-poor. I don't know if you are a bit familiar with all of this convergence concept in development, meaning that if you start very low, so your progress normally has to be fast to catch up the delay that you have in certain, compared to people who are, but this is not what they finding in India, for example, when they decompose the MPI result. And this is an example of also of the value added of doing this kind of analysis. Just takes, this kind of facts and know then, okay, so if that's the case, that really means, in the case of India, for example, this poor state of India, which are here, the problem is more than serious, because in addition to being poor, there are also the region in dynamic terms that are performing also so there is no hope, but I don't want to say it in that way. And this dynamic analysis, so here it was geographical decomposition. You can do the dynamic analysis for any other social groups also. They did that also by, like, for example, religious group, Muslim, Hindu, Christian, and by caste also groups. Because these are more or less the kind of sensitive or the relevant group to analyze in this context. So depending on, in your case, as Jose was saying also, it could be rural versus urban area, and you can see really what, depending on what you have in your research agenda or the different questions that you have in mind. This is a bit, again, the more visibility or variability that you get when you do a subnational decomposition. So here we're plotting here MPI, the variation of MPI for different countries by different region of the world. So you see here when we use national data, for example, let me just take the example of South Asia here. With national data, this is just the interval within which the MPI varies. But if you use subnational data, you see the interval goes up very quickly. So you have more information, and with this more detailed information, you're able to really get, interesting history and relevant facts for your analysis. The same, so if you try, for example, to plot the MPI data at the global level, you have some variabilities, from one country to another. If you do the same maps using subnational MPI, you get something which is more precise. So this is more or less what I wanted to remind and to say very quickly about the population subgroup decomposability. So before we see the dimensional breakdown, let's revise very quickly some of the notion. So what is the difference between the uncensored Hitcon ratio and the censored Hitcon ratio? Yes, please, one at a time.
The censored is deprived and poor, and the uncensored is just deprived in one dimension.
Okay, so meaning that can the uncensored Hitcon ratio of a dimension be lower than its censored Hitcon ratio? No, because the censored Hitcon ratio, in addition to being deprived in that dimension, there is an additional condition, which is to be multidimensionally poor, meaning that here you have two conditions and here you just have one. So the case where you have two conditions is obviously lower than the case with one condition, right? Can the censored Hitcon ratio of a dimension be higher than the multidimensional Hitcon ratio?
Yeah.
No, it's also the same. But the only thing is, for the multidimensional Hitcon ratio, let's say that you have one condition, and for the censored Hitcon ratio you have two, because you have to be multidimensionally poor and also deprived in that dimension. Right? What is the relationship between the censored Hitcon ratio and M0?
It's the same.
So H multiplied A is M0.
Sorry?
Censored head count ratio is H, and then if we multiply that one with A, and then it just gives us M0.
No, I
So
mean,
you're reading uncensored heat count.
yeah, censored head count ratio is that just I mean, M0? What is M0? M0 is the multidimensional poverty index, which is A times H, right?
Mm-hmm.
And H is the, I think there's a confusion with terminology for me sometimes, but
So this is
censored head count ratio is not H, right?
Mm-hmm.
Isn't that the sum, N0 is the sum of Wj over dE times the censored head count ratio?
The terminology
Exactly.
is different.
Because the censored heat count are just like you have
What
log
is
of
H? H is the
poverty
head count
per
ratio.
dimension,
censored head count.
or kind of you have log of M0 per dimension.
Right, it's not censored.
So,
Yeah.
because M0 is a weighted sum of censored heat count ratio. Now,
So can you tell us the answer again?
yeah, M0 is a weighted sum of censored heat count ratio, because the censored heat count ratio you can see them as just blocks of your M0 both per dimension or per indicators.
Okay. So the censored head count ratio, are we talking about within a dimension here, or within a dimension?
Yeah, it's always for all of these censored
It's
and
within a
uncensored, it's
dimension,
always
right?
per,
Okay,
per
cool,
dimension.
cool. Yes.
What kind of policy analysis can be conducted using the censored? This is what we will try to see in the next 10 minutes. So before we see the dimensional breakdown, very quickly again, a practical example here where you have 4 dimensions and the deprivation vector for 4 persons, and then we get the deprivation matrix, very clear. And then from the deprivation matrix, so now we want to think from a column perspective, so from a dimensional perspective. So if you want to think from a dimensional perspective, the first thing that you can do is to get the uncensored heat count ratio, which is just thinking about deprivation, but more or less in a unidimensional context, just to see for each of the dimensions if the person is deprived or not deprived. And this is why also when you started working in Theta, this is the first computation that you did, because this is the first thing to say. So this is my population, and in my population, these are the summary statistics in general, and for this variable, this is what I get, for this is what I get, just to describe the population. So to get the uncensored heat count ratio per dimension, you just have to see who are deprived over the total number of persons. So here you will get 2 persons deprived in income over 4, you get 2 over 4. Year of schooling, 2 persons deprived over 4, you get 2 over 4. And sanitation, you have 1 person deprived out of the 4, you get 1 out of the 4. And electricity, you get 2 out of the 4. And you can read them also. And then if you want to get, so observe here that for the uncensored heat count, we don't need weights to get the uncensored heat count, because you're thinking in just a unidimensional way. So if you think in unidimensional, you're just focusing on one dimension at the time. So you don't need to know what is the relative trade-off, or ways that this dimension have relative to the others. So once you want to go beyond this, beyond the uncensored, and you want to get the censored heat count, so now you have to run the whole process. Because to get the censored heat count ratio, you have to know who is poor and who is not poor multidimensionally. And to know who is poor and who is not poor, you have to run the whole process, which is taking your deprivation matrix and then getting the weighted deprivation matrix, and then the counting vector, and then the identification if the person is poor or not poor using the poverty cutoff. So this is what we need to do here. So if we use this weighted this weight vector, we get a weighted deprivation matrix. And from the weighted deprivation matrix, we construct the deprivation score vector, which is here, that we already did before. And we compare each of the score to the poverty cutoff to say if the person is poor or not poor. And once, so these are the two poor people if we use a cutoff of 1/2. So these are our two people because their deprivation is equal to the poverty cutoff or greater than the poverty cutoff. And then before we get the censored heat con ratio and the M0, we have to censor. So kind of ignoring the non-poor and focusing only on the poor. So we will replace this line by 0 to get the censored deprivation matrix. So this is the step that we skipped a few minutes ago because we didn't have a pool. So in this case, we have this one who is a non-pool. So he gets directly, we censored to give him 0. And then if you calculate your M0, it's an average over the censored deprivation score vector, which is 1 plus 1/2 divided by 4. And then you get 6 over 16. Now, how do you decompose then this M0 per dimension? To do this, then you want now to redo, to compute the M0 for each one, or which is more the chair times the censored heat cons. To get the censored heat con, you censor first. So from here we do this, and then now we can get the censored heat con ratio, which is exactly as the uncensored heat con ratio, but the only difference that if you have any non-poor person in your vector, you have to put 0 for him. So if I come back here, let's take the case of the income. We know that person 2 is non-poor. So to get the uncensored, we just take who is poor versus the total number. To get the censored heat con, we have to put 0 here because this person is not poor. So then we get as censored heat con for income is just 1 poor out of the 4. And then year of schooling the same. We get 1 out of the 4 without.
Year of education should be 2 over 4, right?
Sorry?
You have it over there. Yeah, you're right. It's over
Yeah, year of education 2 over 4, and so on. Just to show you again, you see, for example, when we are analyzing year of schooling, the second person is non-poor, but in any case, is not deprived in education. So for him, the censored and the uncensored heat con are equal. But for the first person, they are different because the second person here is not multidimensionally poor, but he's deprived in income. And then once you get the censored heat con ratio, you can do the decomposition now, which is your M0 is the weighted sum of your censored heat con ratio, which is what I was just saying a few minutes ago, that the censored heat cons times the weights, the relative weights, give you more or less the level of poverty as measured, just if you want to use that dimension. And then you get the contribution by taking then the censored heat con times the relative weight divided by M0, which just gives you the relative contribution. So what is what is the size of this poverty as driven by this dimension, or divide over, respective or relative to the overall poverty. And in the union approach, what is the relationship between M0 and uncensored Hitcon ratio?
It's the sum of M0 will be the weighted sum of uncensored composition.
Exactly. Because in the case of union approach, the uncensored Hitcon and the censored are the same. Because in a union approach, you cannot be deprived in one dimension and be non-multidimensionally poor. So once you are deprived in any of the dimension, systematically you are also multidimensionally poor. Implying that if you take the intersection between being multidimensionally poor and being deprived in any one of the dimension, you get the same. So now, in terms of numbers, so then how do we compute the contribution? We said is the weight, the relative weight, times the censored heat count divided by M0. And this is the case of, I think, year of schooling. Right? Is it very clear? So you are like eager to go on Stata because all the theories are fine now. You want to program it in Stata and compute now. Now, I already show you some examples with data when you do the decomposition by subgroup. And when you do decomposition by dimension indicators also is very important because usually, most of the time what happens, the aggregate number that you get in M0, if you try to compare different, population or countries, when you don't do this decomposition, you don't have the whole story because you can get, for example, what we have in here, you have a similar level of MPI, but with different composition of poverty. So if you take the case of these three regions, they all have the same level of MPI, but when you see the composition is different. So in the case of Bangladesh here, the region of Bangladesh, the share of education is just around 17%. And in Nicaragua, in this region, is more than 20%, almost 30%, and over there is a bit less than 20%. And you can see, for example, that in Nicaragua, the main thing is the living standard, which has a very huge share. So at least when you do this dimensional breakdown, you know exactly which dimension drive or your poverty in the things that you're analyzing. And the things you need to keep in mind also, I already discussed with some of you, is that when we always say contribution is using the dimension, is really like the multidimensional poverty. Let's say you have a solid things, which is multidimensional poverty, which is made with different blocks of different phase or type of poverty. This is poverty in health, this is poverty in education, this is poverty in living standard, and you put them together to get a solid total ball, which is the multidimensional poverty. So these contributions mainly are telling you what is the size of each of these phases of poverty in your multidimensional poverty. Because given that you're analyzing multidimensional poverty, so you are really putting together different phases of poverty. So by putting these together, what are like the importance of each of these, problems? Or you can also have different level of MPI, but with same composition, which is the case of what we have here for these three regions. They have different level of MPI, but in terms of composition or the contribution of each of the dimensions, we're getting the same the same result. This means that when you're reading your result, you have to first look the aggregate numbers and then go below the aggregate number to see whether there is any story that you can get behind and so on. This is another way to, graphical way to see the decomposition or the disparities, the contribution for different indicators or dimension. So you can plot this, how you call it, spider to see like which of the dimension has huge contribution or not. So if they all have the same level, you just have a cycle like this. What if they have different contribution, you start having things that are doing like this, and you know. But it's a good visual way also to present things. I will not get into numbers because in any case, we will get into the depth of number when you will present your result and see exactly how you compute them. And this is the composition of poverty for these three countries, Zambia, Nigeria, and Niger. And you can see also that the composition are different from one indicator to another. So you can do this kind of analysis a bit, or say what you were asking. So you can do this, for example, but instead of having countries here, you can do any other subgroup of population, urban versus rural, you see what is going on, or I don't know, any other economic groups or social groups, you see how is the composition of poverty is changing, or do this also for different groups. So this is, for example, the decomposition per region, and in India, for example. And where here you have, where is the education? Given that the authors of this paper is here, I think I'm going to let him read this result. But the idea is here.
It's hiding below somewhere because we didn't reduce the font size enough.
Yeah, this is why I'm not saying also where is the. But I think Delhi, which is the. Shuman, can you read this Delhi and this one?
Yeah, I mean, you could see Delhi is characteristically one is a state and the other is a union capital territory, which is primarily city. So it's probably quite expected that they will have different profiles of deprivations. Kerala is quite well known for their high performance in education. So if you look at the education deprivations, which is the bottom two groups, you will see the contribution of, that particular indicator. Two particular indicators, they're very low. Okay? Delhi, on the other hand, the education deprivation is quite high. That is the contribution. So as a city, it has less asset deprivation in that sense, because it does not have many rural areas. It's mostly urban, and which can be reflected, as you can see, the asset deprivation on the others, or standard of living deprivation, is much higher in Kerala, which consists of rural areas, than in Delhi. It also shows you, so Bouba is presenting these different graphs which sort of give you, so this gives you a thought about the different kind of decompositions and analysis and argument that you can also provide in the particular country that you are using. So that's the main idea behind showing you these different kind of decompositions.
So this is more or less what I wanted to discuss with you in terms of decomposition of NPI by subgroup, by dimension, by crossing the composition by subgroup and by dimension to really get into more detail and see what's going on. And before I take another 10 minutes to show you very quickly how you do all of these things in Stata, I will discuss if you have any question or comments.